Namaste everyone. My name is Shreya Singh, BSc second year, roll number 205063. Today I am going to do the presentation of Mathematics Mechanics paper number 2. Here are the topics covered in the presentation, that is theory of equilibrium, condition of equilibrium, example of equilibrium, types of equilibrium, that is stable equilibrium, unstable equilibrium. Another topic is application of theory of equilibrium on strings, application of theory of equilibrium on system of forces, points at central axis, application of theory of equilibrium on virtual work. Let us start with understanding the theory of equilibrium. An object resting on a surface and the corresponding free body diagram showing the forces acting on the object. The normal force N is equals to opposite and collinear to gravitational force mg, so that the net force and moment is zero. Consequently, the object is in the state of static mechanical equilibrium. The types of equilibrium, that is stable equilibrium and unstable equilibrium. Let us understand with the definition, that is, let a body be slightly displaced from its position of equilibrium, then the equilibrium is said to be first stable if the forces acting on the body brings it to the original position. You can see in the diagram below that we take a ball here and keep a ball and apply force in both the direction, that means right and left direction. The ball remains stable at the lowest position of the bowl, that means at the bottom of the bowl at the bottom of the bowl the ball remains stable. And in the second one, uh, make the ball upside down and keep the ball at the topmost position of the bowl, the ball is in unstable motion, as it will always try to come to the lower end of the bowl. And the third one is neutral. If we keep a ball on a flat surface and apply a force in left and right direction, the ball will always remain in equilibrium position. That means we have three types of equilibrium. First is stable, then unstable, and then neutral. And for stable, if the forces acting on the body brings it to the original position, it is called stable. And if the forces acting on the body brings it away from the original position, that is unstable. And neutral, if the forces acting on the body remain it always in the position of equilibrium, it is known as neutral equilibrium. Now, the stability or instability of body with its center of gravity. Let us take three cases. In the first case, if center of gravity lies on the vertical line through the point of contact and it is below the geometric center, that means when you see in the figure, the center of gravity lies below the geometric center of the circle. So, and the sphere is slightly displaced and it tends to come back to its original position of rest. This is called stable equilibrium. Now, in case 2, if center of gravity lies on the vertical line through the point of contact and it is above the geometric center of the sphere as shown in the figure, and sphere is slightly displaced, then it tends to go away from its original position of rest. This position is known as unstable equilibrium. And the third case, if center of gravity lie on a vertical line through the point of contact and coincides with geometric center of the sphere, is slightly displaced, when it will remain in equilibrium. In this case, equilibrium is neutral. Like in this sphere, when the center of gravity is below the geometrical center, it is stable equilibrium. And when the center of gravity is above the geometric center of the sphere, then it is unstable. And if the center of gravity and the center of geometrical center of the sphere coincides, then it is neutral equilibrium. Now, how to determine the nature of stability? Let Z be the height of center of gravity of a body from point of contact. Express x in terms of x in turn or vertical, then the position of rest is given by dz upon d theta is equals to 0. which on solving gives theta is equals to alpha 1, alpha 2, alpha 3 and so on as the position of equilibrium. Now the equilibrium is stable at theta is equals to alpha if d square z and d theta square is greater than 0, that means double derivative of z is greater than 0, then which is at theta is equals to theta 1. So here you have a stable equilibrium, and when the double derivative is smaller than 0 and theta is equals to alpha 1, however d square z upon d theta square is equals to 0 for and for theta is equals to alpha 1, then we consider d cube z, d theta cube and d4 z upon d theta 4, that means third and fourth derivative of z. And for the position of rest, d cube z upon d theta cube, the equilibrium stable or unstable according as d4z d theta 4, that means fourth derivative of z is greater than 0 or less than 0 at angle theta is equals to alpha 1. Now we have to note here a point that if z represent the depth of center of gravity of the body, some fixed horizontal plane, then the equilibrium stable if then if the second derivative of z is smaller than 0, and that means at angle theta is equals to alpha, and unstable if double derivative of z at is unstable if double derivative of z is greater than 0 at theta is equals to alpha 1. Now energy test of stability. Let us understand a point that for a system of equilibrium under conservative forces, the potential energy is minimum for stable equilibrium, whereas the potential energy is maximum for unstable equilibrium. Here are some general conditions for stability of a body resting on another body. When a body rests on another body, as you can see in the figure, there is a sphere resting on a bigger sphere. The height from both the geometrical center is given as h. Now the equilibrium is stable if 1 upon h is greater than the sum of 1 upon small r, that means radius of the smaller sphere, and 1 upon capital R, that means radius of the larger sphere. That means when we sum the if we sum the radius of 1 upon the radius of both the sphere, when it comes smaller than 1 upon h, then the equilibrium is stable, and if 1 upon h is smaller than 1 upon small r plus 1 upon capital R, then that equilibrium is known as unstable, where h is the height of center of gravity of upper part from the point of contact. Now we come to our next topic, that means applications of theory of equilibrium on strings. Equilibrium of strings. Let us understand with the definition that if the weight per unit length of the chain or string is constant, the quaternary is called uniform or common quaternary. Equation of cotton quaternary. Now we will see the equation of cotton quaternary. Let us take ACB, a uniform heavy flexible card. That means if we take this ACB, a uniform flexible card attached to a point A and B at the same level, these 2 points are on the same level, and C being the lowest of the chord, that means this part is the lowest of the chord. Draw CO vertical and OX horizontal, and take OX as x-axis and OC as y-axis. Now we took those these y-axis and this x-axis. So let P be any point of the string so that the length of the arc CP is equals to S. Let W be the weight per unit length of the chain. Now consider the equilibrium of portion CP of the chain. The forces acting on it are tension T0 acting along the tangent at C, and which is therefore horizontal. Tension T acting at P along the tangent at P, making an angle xi with OX. Its weight WS acting vertically downwards through the center of gravity of the arc CP. For equilibrium, these three forces are must to be concurrent. Hence, the line of action of the weight we must pass through the point of intersection of T and T0. Not resolving horizontally and vertically, we have T cos xi is equals to T0 and T sin xi is equals to Ws, and which gives us tan xi is equals to Ws upon T0. We shall write T0 as Wc, where C is a constant, and tan xi is equals to S upon C. which gives us S is equals to C tensile, which is the intrinsic equation. We get S is equals to C tensile, which is the intrinsic equation of quaternary. Now, system of forces and its type. A force system is a collection of forces acting at specified location, may also include couple. Thus, the set of forces shown on any free body diagram makes up a force system. Force system is simply a term used to describe a group of forces. The types of forces system are given, we will discuss only two, that means coplanar and non-coplanar force system, and concurrent and non-concurrent force system. Let us understand the coplanar and non-coplanar force system. The force system in which all forces are acting in same plane are known as coplanar force, whereas system in which forces acting in different planes are known as non-coplanar force system. Concurrent and non-concurrent force system, that means the forces which are passing through a common point are called a concurrent forces system, whereas forces which do not pass through a common point are non-concurrent forces. That means the force system in which all forces are on same plane, then it's known as coplanar, and if they are not in the same plane, then they are known as non-coplanar. And if all those forces which pass through a common point, then that is known as a concurrent force, and if they do not pass through the common line, then it's always a non-concurrent force. Now we'll discuss some more definition about, that is, points or central axis, a line through a rigid body which is parallel to the vector sum of F of the system of forces acting on the body, and which is located so that the system of forces is equivalent to force F applied anywhere along the line, plus a couple whose torque is equal to the component of the total torque T exerted by the system in the direction F. Now, central axis. If a system of forces reduced to single force system and a single couple in such a way that the axis of couple coincides with the line of action of the force, then the line is known as central axis. Wrench and pitches. If a system of forces is reduced to single force R and couple having moment K whose axis coincides with the direction of the force, then R, K is known as wrench with the direction of the force of system. The ratio K upon R is called the pitch of the system. Screw. A straight line along with the acting force when considered together with pitch is known as screw. Now, virtual work. What are virtual work? So, when multiple force applied on system provide no change in displacement, also no geometrical change in the body, then that work is known as virtual work. Total virtual work is obviously zero because it requires no displacement, and when there is no displacement, there is no work done. So, virtual work done by a rigid body. If a system of coplanar forces acting upon a rigid body, now we just understood in the previous part that what are coplanar. Coplanar are those forces in the force system in which all forces act on the same plane. So those forces, if a system of coplanar forces acting upon a rigid body keep the body in equilibrium, and if body is given a slight virtual displacement consistent with geometrical conditions of the system, the algebraic sum of the virtual work done by the forces is zero. Conversely, if the algebraic sum is zero, then the forces will be in equilibrium. So you can see in this diagram that the necessary and sufficient condition that a particle acted upon by a number of coplanar forces be in equilibrium is that the sum of virtual work done by the forces in small displacement consistent with geometrical conditions of the system is zero. Now if we'll resolve these forces, then we'll get alpha sigma x plus beta sigma y is equals to 0, and which will provide us the equation of virtual work, that means summation of x is equals to 0 and summation of all the forces in y axis is equals to 0. So basically we get total virtual work is equals to 0. Now let us solve an example of virtual work. 4 equal heavy uniform rods are joined are freely jointed so as to form a rhombus, which is freely suspended by angular point, and the middle points of the two upper rods are connected by a light rod so that the rhombus cannot collapse. Like this is a rhombus. These points are freely jointed, and one line is one light rod is attached from L to M. This is the light rod, and this is the rhombus provided to us. This rod helps the rhombus not to collapse. Prove that the tension in the light rod is 4 W tan alpha, where W is the weight of each rod. That means W is the weight of each rods. That means A to B, B to C, C to D, and D to A, also L to M. So W is the weight of each rod, and 2 alpha is the angle of rhombus of the point of suspension. That means this 2 alpha is the angle of rhombus at the point of suspension. Okay, so this is 2 alpha. So on the single part is when both of these angles combine, they make angle 2 alpha. So the single angle is alpha. Now giving a slight displacement to the system and changes to A alpha, A plus delta A, work done by weights is 4 W delta AG is equals to 4 W delta 2A cos alpha. So virtual work done by the system is 4 W sigma 2 alpha 2A cos alpha plus T sigma 2A sin alpha is equals to 0, which implies to minus 8A W sin A delta A plus 2AT cos A delta A is equals to 0, but delta A is not equals to 0. Then which implies us minus 8A W sin alpha plus 2AT cos alpha is equals to 0, which further gives us T is equals to 4 W tan alpha. In this system there are 4 heavy rods, each weighs W, so the combined weight of center of gravity is in positive. That means 4 W as fixed downwards, So the weight exerted by all the 4 rods at the center of gravity of here at G will be 4 W downwards. Thank you.